Hello, everyone. Before I start, you guys have any questions about anything? Any questions? Okay, so we're gonna pick up where we left last time. So basically today I'm gonna finalize how to prove things using the idea of a set. Okay, and our basic idea is that if you have any sets, regardless what they are, to prove that a subset A is in B, we proceed as follow. We take an arbitrary element in A. We take let X be in A and we do stuff. And then we show that X must be in B. That's really our approach. Okay, so today we're gonna do more problems along those lines to make you feel comfortable with that. So my first problem is, all of them are simple in nature. So let A and B be subset of a universe U, of a universal set U. Okay. So I want you to prove the following. Again, we're going to do it together, that the power set of A union the power set of B is a subset of the power set of A union B. Okay, it's not a hard problem, it's just practice every single idea. All right, so we get started. So this is a first set, and I want to show that it's a subset of that. So the approach, as usual, we take an arbitrary element in here, and we basically have to show that this element is here as well. All right, so who would like to take the lead? Who would like to take the lead? So we're gonna start B. Let something be an element of this, of the power set of A union the power set of B. All right, so I'm gonna call it, since we know that the elements of power set are sets, so instead of calling it little x or little a, because we know ahead of time that we are actually working with set, we say let x be in the power set of A union B. Okay, and then what should we say? I will start. Just pick a student. Nick, would you like to take over?
I was actually not able to make last class, so this is kind of new material.
Oh, okay.
So not quite in lead.
Don't worry about it. Don't worry about it. Just be with us, okay? Don't worry about it. Okay, Simon, you would like to take the lead.
Okay, so let X be in power set of A union power set of B. Then X is in the power set of A, or X is in the power set of B.
X is in here, or X is in here. And this is by definition of what?
By the definition of union.
Right. Every time we have to say, what does this mean? So that's really what we said, by the definition of union. So it's either in here, we don't know where, either in here or in here. Okay, keep going.
So then we have two cases.
Because we have an or, it means I don't know where my X is. It could be here or here. So two cases.
So I guess the first case would be X is in the power set of A.
Case one, assume X is an element of the power set of A. Now we analyze. What does this mean? Very careful. And remember, that's my goal. My goal is here. That's where I would like to get. That's where I have to convince you that where my X is. All right, so let X be an element of the power set of B. What does it mean? Simon, would you like to keep going?
I'm kind of stuck.
I know, that's why I'm bringing this setup. I know that you guys always get stuck with that. Okay, what does it mean to be an element of the power set? What does it mean? Tim, would you like to pitch in?
This means that X is a subset of A.
Crucial. You guys drill this in your head. Pure and simple. The element of the power set are the subset of A. Because when I ask you fairly simply, what's P of 1, 2? What do? You just list the stuff. What is it you're listing? You're listing all the subset of 1, 2. That's what the power set means. That's exactly what you do. So an element in the power set means X is a subset of A. Okay, so please, if you're writing, you're doing anything, just focus on that. Drill this. That's what the power set. They are subset of A. All right? So now assume X is in P of A, power set of A. Tim, can you finish it for us? And everybody follow.
So since X is in the power set of A, this means that X is a subset of A.
Very good. This means, and verbatim I'm writing, this means that X is a subset of A. You always have to keep your eye on the price. You have to convince me X is in here. Keep going. Remember, that's what you have. This is the red. That's where you're heading.
So
now
I'm trying to think of how to word it.
What?
I'm trying to think of how to word it.
Okay, just intuitively, what's happening? So this is A, X is in it. It's a subset of it, right? And what do you wanna get to? Anybody can pick up.
What are we proving?
What?
Like I'm coming a little bit late, so
this one, this statement.
okay.
You see it?
So okay.
Yes. So we started here.
Yep.
What do you want to show?
Oh, all right.
Okay. All right. So you want to convince me that it's in the power set of A union B. Keep going. Please, every one of you think with me. That's the only way you learn.
I don't know if I'm jumping ahead, but from there, could we assume that X is a subset of A union B?
Because, you're right, because there is one word, one sentence I wanted.
Because the X is a subset of A, so X is a subset of A union B.
Because A itself.
Oh yeah, it's a subset of A union B, yeah.
Right. A itself is inside A union B. So X is in A, right? And if this is A union B, X is in A. But A is inside A union B, it means X has to be in A union B. We don't really have to prove anything at this stage. I mean, it's really intuitive. So X is in A, but A is inside A union B. So X is a subset of A union B. That's the link, okay? But what does this mean? That's, I'm not done yet. What do you think should be my last sentence? That's where I'm heading.
So the X is in power A union B.
An element.
Yeah,
watch carefully. An element of the power set of A union B. Okay, it's a subset of A union B, has it's an element of the power set of A union B. Okay, so that's how we do it step by step. So let's sum up. Case 2 is verbatim the same, so I'm not going to repeat case 2. Okay, so let us sum up. We start in an element in the set to the left, in here, and then I want to convince you it is in here. So I say, okay, what does it mean to be in the union of things? Union, it means either in the first or the second. So I don't know where it is. So I said it, but I have to show, regardless where it lands, it's going to end up in here. So I say, okay, let me take my first case. Assume it's in here. But what does this mean? I mean, power set is confusing. Means is a subset of A. And I keep my eye here. I never lose track where I'm heading. So it's a subset of A, but A itself is a subset of A union B. So X is going to be a subset of A union B. But what does it mean, a subset of A union B? Is an element of the power set. Okay. Now case 2. Case 2 is assume X in the power set of B, and then basically the same as case 1. I will not repeat it, but it's exactly the same as in case 1. So I have to do the same thing, but instead of B, I put A.
So
Okay.
can we write the same thing in the test, or we have to write this like?
You have to make sure. You have to make sure it's the same.
Oh yeah. Okay.
Yeah. You understand? It has to be verbatim the same.
Okay.
Means here it's the same. Instead of A, I put B. Sometimes the cases are not the same, and we've done this.
So in the exam, we have to write everything out, right? Like X is a subset of B, but B is the subset of A union B.
Yes.
Okay.
Yeah. It's just for you to understand what's really going on. I mean, it's really not for, I don't teach you for the test, guys. I mean, I give you lots of time to take the test. I teach you because to learn. Very good. So any questions along those lines? Now, it's interesting that in this problem, the equality failed. There is no equality. It means if you go from here, you want the end lamp here necessarily. And that will be on your homework. So on your homework, you have basically to convince me that this doesn't hold. Means you have to give me an element, which is, if this doesn't hold, means you have to give me an element which is in the power set of A union B, which is not in here. So on your homework, you will have to show me that you actually have the inclusion go one way, it doesn't go in the other way. But I need this as a homework. All right. Again, the same ideas. I'm not really moving at all. I'm still hammering you with the same concepts. So my second problem is the following. Okay, so let me change paper to be neater. My second problem is, so again, I have A, B, and C. They are a subset. I'm going to make the same universe of a universal set U. So A is in U, B is in U, so that is a universe. And I'm going to look at the following. I want you to prove the following. A, Cartesian. Now, you have not to start remembering. What does the Cartesian represent? Okay, it's equal to A, the Cartesian product of A intersect B and A intersect C. Okay, so that's what we would like to show today. So A, the Cartesian product of A and B intersect C is A intersect B, Cartesian product A intersect C. So that's really what I'm hoping to accomplish today. So to be able to do that, let us remember first. If you have two sets, I'm going to call them C and D, not necessarily A and B. Let us remember, what's the definition of the Cartesian product? It means the element of the Cartesian product are what? Question addressed to you. What's the Cartesian product? Don't make me pick. Okay, what's the Cartesian product?
So say if it was like, if C was like 0, 1 and
right,
like
that's
1, 0.
Yeah, but in general, they are all the ordered pair. You can give them whatever name I want. CD, such that the first is an element of C, the second is an element of D. So we cannot work with anything unless you know really its definition. So the Cartesian product is all the ordered pair CD, where the first is in C, the second is in D. Now, the universe, so if C is a subset of U and D is a subset of U, for example, then, no, actually, then that doesn't have to be U. Let me call it V. Then the universal set for C cross D is actually U cross V. So that's the universal set. Okay. So now that I reviewed the Cartesian product, because we have to understand it, I go back to our problem and we're going to prove it. So that's a quick off recall. Okay, we recall that. May I move on? Now, back to here. So A, B, C are subset of a universal set U. I want to show that the Cartesian product of A cross this is there is some kind of distributivity property in a way. So it's A intersect B cross A intersect C. So I have two sets. I want to show them equal to each other. Okay, so I need two inclusion to proceed there. So I have to show that every element, first we're going to show this inclusion and then the other one. So I'm going to focus on this one first. So let us prove that. It's actually fairly simple. It's not hard, but what matters to me now is how to understand how do we get started. All right, so let, and now let what? Something in the first set. And somehow I have to convince you that the something that you have to tell me what it is, if it is in this set, it has to land in here. All right, what shall I write here? I kept it open for you.
It would have to be an ordered pair, right? So
it has to be an ordered pair.
So you could say like X, Y.
I don't, X, Y, exactly.
And then X has to be an A, while Y has to be B and C.
So you have to start with an ordered pair. Why you have to start with an ordered pair? Because the elements here are ordered pair. So that's the, that's what the elements are. So we have to start with an ordered pair. After that, it's going to follow very, very simply. Okay. Then keep going. Whoever was talking, then, and that's my goal. As I said, you never reach, always I emphasize where I'm heading. Otherwise, I am in trouble if I know where I'm heading. So that's really where I am heading. All right, so let XY be in this. Then what? Rachel, do you think you can take the lead? Rachel?
I'm slowly following.
All right, no problem. Who would like to take the lead?
Then X is an element of A and Y is an element of B.
Okay, slow down, okay, I'll write what you, then X belongs to A,
Yeah.
but that's the definition.
Yes.
And Y?
And Y belong to B, interest C.
By what?
By, I cannot read it.
By the definition?
Of the interrupt.
No, what do you call this?
I don't know how to call it, sorry.
Cartesian.
Okay, Cartesian.
Yeah. It's come from the name Descartes. Whatever, Cartesian product.
I keep calling them a multiply.
Ah, you call them, no, we call them Cartesian product.
Okay.
Right, okay. It's like the Cartesian plane. Like this is, the XY is called the Cartesian plane. Yeah. You know, every element XY we call the Cartesian plane. Very good. So X is in A and Y in B intersect C. Remember where you're heading. So what you want to prove that that's those pair, ordered pair is in A intersect B cross A intersect C. Oh no, I wrote nonsense. Why did I write nonsense here? My apology. My apology. Sorry.
Now it's easy. Like
I know. I was looking at it. I said, what did I write there? Okay. My apology for that. That's why you should write pencil in math, not okay. So X is in A, and now I have to convince you that my X, my pair, is in A cross B and in A cross C. Now it should be basically fairly simple. So if X is in A and X, Y in C, it means X is in A.
Yeah, and Y is in B and Y is in C.
Y is in B and
Y is in C.
Y is in C.
Okay,
So-
so look at the in cartesian product B.
So X, Y,
in- yeah,
makes sense now. By definition, the Cartesian product. And
X and Y in A cartesian product C.
yeah,
So X and Y in
A cross B.
congestive B.
A cross B. If you want to
Into-
intersect,
Yeah.
end of the problem. Okay, so we're starting with any element in here. It really makes sense. X is in A and Y is in B intersect C. So basically I'm telling you it means your Y is in B and is in C. So your XY is going to be in A cross B and it's going to be in A cross C. Hence the other proof. Now we're going to move the other way around, which is going to be fairly similar. So now the other one. We're going to show that if you take A cross B, intersect it with A cross C. So if I start with an element in here, then this element is in A cross B intersect C. Okay, because that's inequality, so we have to include. All right, so let us start with that. So again, I need to start with an element in here. And somehow I show you that this element, and logically, and using the definitions, then this element is also in here. So I start with an element. So I say let in here. Okay, but now we know that I'm talking about the intersection of two Cartesian products. And I know Cartesian products, the elements are ordered pair. So I start with an ordered pair. So I say let xy be in here. And I have to convince you that my xy is actually in here. So that's really my goal. That's my end point. That's really what my goal is. All right. I would like to get started. Again, follow the definition. Verbatim, we follow the definition.
So X and Y is element of A cas B, and X and Y is element of A cas C.
By definition of
Definition of the
intersection.
intercept.
Absolutely. Okay. Now remember your goal. If you lose track of where you're heading, you don't know where you're heading. I mean, that's things all the time. So I'll keep this here because I need to know where I'm heading. So now I want to convince you that my xy is in A cross B intersect C. Means I have to convince you that my x is in A and my y is actually in B intersect C. That's really what I have to convince you, which is actually not very hard. So let's keep at it. So xy in A cross B, so it means that
X in A and Y in B.
so x is in A and y is in B.
And Y is in C.
Also, x is in A. This one tells me x is in A. I know that already. And y is in C. So I'm just actually verbatim trying to understand the meaning of this cross product. So we put those together. So my x is definitely in A. And since Y is in B and in C, and since Y is in B and it is in C, so my X is in A and my Y is in B intersect C. So my pair, ordered pair, is in A cross B intersect C by the definition of cross product or Cartesian product. Okay. Questions? Okay, so the more we do those problems, the more you guys will have. So of course, you're going to have a homework where you will have to start doing this. And the idea is that, you know, we start trying to relate. If you start from an element in here, how can I show it is in here? So you start watching those elements. What's really going on? And how can you convince me it is here? So now we're going to do again the same spirit with a slight twist, not a hard twist, but a very simple twist. Okay. So again, I will working with set, and the idea is how to work with it. So sometimes I call this if-then statement using sets. You will understand what I am talking about. All right. Okay. Suppose I tell you prove the following. Okay, very, very simple statement. Very simple. Let A and B be subset of a universal set U. So I'm working with two sets. Show that. If A, actually I want three sets, A, B, C. If A, under this condition, if A is a subset of B, and then if I take A cross product C, it's a subset of, what do you think I'm going to write? What do you think I'm going to write? The most natural thing comes to your mind. If A is in B,
B cross C,
it have to be B cross C. Okay, fairly simple statement. The question is, how do we prove those kind of if-then statement? So this is basically, if you want, this is my hypothesis. Okay, that's what I have, that I know that A inside B, and that's really my goal. That's really the goal. That's the conclusion. Or basically the goal. That's really what I want you to show. So here the idea is, we have to use, so I'm write this in Word. So here basically, I need to use, so we're going to assume this. I'm going to assume A is a subset of B. And we're going to prove that A cross C is a subset of B cross C. Okay. All right, how do we show something like that? It's like an if-then statement using where sets are involved. It's actually like we did a proof, a regular proof. Means we're going to assume the hypothesis and we have to show the conclusion. But now the conclusion is an inclusion between two sets. So how can I really show this kind of conclusion? So let me close this a little bit. Let me just hide this a little bit. This is a typical kind of conclusion. How can we show it? If I tell you show n even, for example, you have to show me that n equal to k. If I show you, I give you this conclusion, how do you prove it? Since it's inclusion between set, to show this conclusion, you have to start with an element in here, and you have to convince me that this element is here using the assumption A inside B. Okay, so this type of conclusion, to prove it, I have to prove inclusion between two sets. So it means I have to use the mechanism I did before. So I'm going to start here, show that the element is in here, under the assumption A is a subset of B. So I will do the first problem, and then you guys will do. So how do we prove that? Remember, that's what I want to prove. which is very specific type of proof. So I'm going to start with an element in here. We're going to start with an element in here, but that's what I want to prove. And using our hypothesis, we will show that's the mechanism. We will show that my element is in B cross C. So that's how we're going to proceed with that. Because that's the type of conclusion is inclusion between two sets. The way we prove this, we take an element in here, we use our hypothesis, and we show that it is in B cross C. So that's really the process we would follow. All right, let's do that now. So now the proof. Okay, let XY be in A cross C. And now I want to show that XY is in B cross C using the hypothesis. So if XY is in A cross C, what does this mean? It means that X is in A and Y is in C. That's the definition of Cartesian product. Okay. Now, I have to show you that XY is in B cross C. Okay. But now I have a hypothesis that tells me that A is a subset of B. So, but A is a subset of B. So my X in here, X is in B. So I start with XY in A cross C. It means X is in A, Y is in C. But since A is a subset of B, it means my X is also in B. So now my XY is in B cross C. Right? So if we have a statement like that, if A is a subset of B, then prove this conclusion. My conclusion is inclusion between sets. So to prove a statement like this, I have to show that every element in here is in B cross C, but to go from here to here, I have to use my hypothesis. That's really how we do it. And that's verbatim what I did. Okay, if it's in A cross C, it means X is in A, but if A inside B, it means my X has to be in B. So my XY has to be in B cross C. Okay, so I did the first one. Now I want you guys to start interacting with the second one along the same line. Right, so my second problem is the following. Again, let A and B be subset of a universe. Prove that if A is a subset of B, then the power set of A is a subset of the power set of B. So I'll give you 2 minutes to interact. If you have a scratch piece of paper, think a little bit, how did I do the previous one and how we're gonna basically imitate the process. So that's what I did before with different things. So I'll give you a minute or two to interact with it, all of you, and then I proceed. All right, are we a little bit ready? So this is what I have, and this is really what I want to prove. Okay, so I rewrite a word, so we need to show, basically, this is to remind, that's what we need to show. We need to show that the power set of A is a subset of the power set of B under the hypothesis that A is a subset of B. So that's really what I want. It's an if-then proof. That's what I want to show. So basically, I have to show this kind of inclusion. That's the inclusion I need to prove under this condition. But that's really what my goal is. This is a type of inclusion. So what's going to be my first? So that's what I want under this hypothesis. So what's going to be my first line, do you think?
Assumes the X is element. Oh no. Oh yeah, it's element of A.
Do we agree with him? What do you want to prove? But please be very careful because I always shouldn't get confused here. What is it we really want to show?
Wouldn't
my
we
bad.
want X
What?
be an element of the power set of A?
Right. We have to show that the power set of A is in here. Not A is in here. That's given to you. That's given. That's what you have to show. So where do we have to start? We have to start here and end up here. In the meantime, I use my hypothesis. So be very, very careful. What I want is this in here. Means I have to start with an element in the power set of A. I have to convince you it is in the power set of B, but under this condition. Otherwise, it's nonsense. So what I start is in here. That's where I should start. But that's what I really want to prove. Not that. I don't want to show A inside B. That's not what I want. I want to prove this one. So I have to start with an element in the power set of A, and I want to show you that it is in the power set of B. And from here to here, I have to use logic, definition, and my hypothesis. That's really how it works. All right, now you guys take over. I think you can.
So that implies that X is a subset of A.
Let X be hence X is a subset of A.
And then, but A is a subset of B.
Now I'm
So
using my hypothesis. Now I am using my hypothesis, which is I need it. Keep going.
now that tells us that X is a subset of B, which gives us the conclusion that X is an element of the power set of B.
Absolutely correct. Okay, so we have to be very careful. That's really what I want to show. That's really my goal. So that's an inclusion between sets. How to show inclusion between sets? I start with an element in here. I have to show that it is in here. That's really how it works. All right. Now, another one, slightly harder, but it's okay. I'm going to actually prove the converse. I'm going to prove the converse using the same approach because that's the approach I'm trying to actually work with you today. Prove that if the power set of A, so there are several ways of doing this problem, but this one I want to do it using the approach I'm trying to say. So if the power set of A is a subset of the power set of B, then A is a subset of B. Okay, so what is my goal here? That's the inclusion I want to use, and that's the hypothesis. So that's I need to use in my proof, like we did right here. We used it, but we don't start with it because that's what I want to show you. So what should be my first sentence? Okay. All right, what do you think should be my first sentence?
Let X be an A.
Let X be an A. Why? Because that's what I want to prove. A inside B. What should be my last sentence?
That X is in B.
In B. What should I do from here to here? Use whatever definitions, logic. Here, I use my hypothesis to get from here to here. Okay, that's really how we're gonna show, because that's what I want. I want A inside B. It means I want everything in here to be in here. So that's really my goal. All right, this is a little bit tricky. Let's see if you guys can do it. Let X be in A. How I'm gonna bring the power set of A from an element of A. It's a little bit tricky. Let's see if you guys can nail it down.
If the X is an element of A, so I think the X can be the like one set. So X can be a set of the power of A.
Okay, I want the notation to be crystal clear because you are correct. I want the notation. I'm not writing. I want you to write. I want to write what you said correctly. What do you want me to write? Or anybody?
I think he's going for the set containing X is a subset of A.
Yeah.
And that implies that the set containing X would be within the power set of A.
Very good. Now we are doing great. Let X be in A. It means the set that consists of the singleton X is in A. Hence, X. Now that's a set. Be very careful. Is an element of the power set of A. Watch carefully how the notation is changing. But the power set of A is a subset of B. Now I'm using my hypothesis. So X, the singleton X, is in the power set of A. But power set of A is inside power set of B. It means the single X now is an element of the power set of B. So it's in here. It means the singleton X is an element of the power set of E. So with hence, it means, what does it mean? It means the singleton X is a subset of B. Watch carefully how I am moving between element and subset. And that's the definition of power set. Exactly. But what does it mean to X is a subset of B? If this is a subset of B, it means every element here is in B. But the only element here is X. Hence, X itself is an element of B, which is exactly what I am doing. Okay, so it required a little bit of a small trick, not a lot, because I want to bring in the power set into the picture, and I only have an element. So I created the set that consists of this element. And then this is in A, hence this is an element of the power set of A, and then I use every step of the way. Okay, so slowly we build up the proof. Of course, it requires a little bit of thinking, but we build it up. Very good. So I would like to do 2 more along those lines. Okay. All right. So let us consider the following question. Okay. Let A and B be always subset of a universe. Of a universal set U. Okay. And I'm going to ask you a question before. Suppose I take A. I take away B from it. So I have the set A. I take away from it everything in B, and I get A back. Okay? Then what can I say?
B is an empty set.
Is it necessary?
It's not necessarily, but B is not a subset of A. Or I guess what I'm trying to say is B doesn't have anything that appears in A.
Okay, how do we write this? Very good. But I want you to write it.
Right.
B minus A equal B.
This is good. This is not bad. But I want to go back to your classmate before.
So B,
What did you say? The student who talked before Kai.
Sorry, I just had somebody come in. I was saying that B, nothing in B appears in A.
How can you write this mathematically?
I said B is not a subset of A, or B is not. What am I trying to say?
No, you're not
How
saying
about-
that.
No,
how
I'm
about,
not.
A intersect B equals the empty set. That's disjoint, correct?
Right. Then A intersect B is the empty set. Okay, what does it mean to say that A and B don't have anything in common? This is A and B. They have nothing in common. It means that intersection is empty. Okay, and that's exactly what I want you to get to it. Are you with me? Are you guys with me?
Yeah.
yeah.
Everybody?
I'm with you, but can I ask a side note question?
You can ask anything you want.
The definition of union we said was that X could be, if it was A union B, it would be X in A or X in B.
Yes.
So do we just dismiss the possibility of it being in the intersection point? Because union is both circles completely, correct?
Union is this. That should be the union, even if they are disjoint.
So if they are intersecting, by definition of union, do we just dismiss the fact that it could be in both and we just say it could only be in one or the other? Am I making sense?
I'm trying to. Repeat
So we
this.
said the definition of union is that X can be an element of A or X can be an element of B.
Yes.
Does that mean it cannot be in
No,
both?
because when is the or true? This go back to definition of or.
If it's true if it's in one or the other.
No.
No. Okay.
What's the truth table for the or?
It's only false when they're both false.
Right.
Okay.
Yeah, are you with me?
Yes.
True, false, true. False, true, true. False, false, false.
Okay.
it's
So
or.
even when you're writing it and you're not doing a case of it being in both, it's because it only has to be in one to be true.
No. X, it means X in A or X in B if you want, or X is in both.
Okay.
That's the union. Okay?
Okay. Thank
Now, because of the definition of or, I don't have to write this necessarily.
Right.
Because if it's in here or in here, it means it's in here or in here or in both. Because or, usually we use what we call the inclusive or. So or is true, not if both of them are true. If one of them is true. Or is true if one of them is true and if both are true.
Okay. I just wanted to clarify that.
That's crucial. That's crucial in the or definition. Okay, so if I tell you X is in A or in B, it means I'm telling you X is in A, or in B, or in both.
Okay.
That's the or in math.
That's
If
what I
tell
thought.
you, if I say Rachel is taking MA 330, I don't know what you're taking. I'm just, writing stuff. And let us say MA 430. Okay, I say Rachel is doing this. What I mean by that, so what the other person should understand, it means she's either taking this or that, or she's taking both. So I'm not telling the student exactly what she's taking. I'm telling you Rachel is in MA this or in that. So it could be that you're in here only. It could be that you're in here only, or it could be that you're in both. That's what the or is.
Okay. I just wanted to clarify because I didn't remember us writing a third case.
Because
Make sure.
I wrote it at the beginning of the semester. I wrote it this way because you did not understand the meaning of or.
Okay.
When I wrote it the second time around, I did not write that. I did that on purpose because I want to remind you that if I said this is here or here, what does it mean for this to be true? This to be true mean either here or in both. So the or statement is true if this is true, or this is true, or both are true. That's why I dropped it the second time around.
Okay, thank you for clarifying.
Oh yeah, this is crucial. This is crucial. That's the or in there. All right, so let me go back to here. So if A minus B is equal to A, it means if I take every element in B from A, I get A. It means A intersect B is empty. Very intuitive. Now prove it. And we're going to prove that something is empty. So I want you to remember, stuff. Showing that something is empty is kind of hard. So how shall we do that?
I would imagine we'd probably use a complement.
I don't understand what do you mean.
I don't know. I'm just thinking because normally when a particular case is difficult, we just go to the remaining stuff. But I don't know if that actually does anything here. Probably doesn't.
If you clarify it, I can help.
I guess I'm still working it out, so I don't know if I even have anything.
Minutes. You
okay,
have to
I
have
was
2
gonna say I don't
minutes
even
to
know if
work
I have
it
anything
out.
to clarify.
Yeah, just go ahead. You have 2 minutes to work it out. Think about the problem. So it's an if-then statement. The conclusion is kind of tricky to prove. So you guys use everything we've learned in a way. Not everything, what we've learned. Any ideas?
I think you want to prove that that A union B is a null set. So like what I'm trying to figure out, let X be an A union B means that X is.
Where did you bring the union from? You have to convince me.
I meant intersect. I got mixed up.
Okay. No, I can. Okay, so go ahead.
It means that. So let X be the A intersect B.
Mm-hmm.
It means X is in A and X is in B. And I think this is the part where you use your hypothesis, where X, but like A minus B equals A. So it would mean that B would not be included, which means that A intersect B is a null set. I know it's probably something like I'm missing.
Yeah, keep going. I want you all to keep thinking.
I have a different idea.
Go ahead.
Like, so let the X is the element of A, and because the A minus the B equal to the A, so the X is not an element of B. So A interrupts B is empty set.
So you prove it that if X is in A, then X is not in B.
Yeah.
And does this mean that A intersect B is empty?
Mm-hmm.
It's not correct.
Not correct.
Why?
Maybe have Y. Okay.
I don't know. I don't have like this fleshed out, but is there a way we could see if there is where A intersect B is not the empty set and it contradicts? Or
That's the best approach.
okay, that's I
Why?
haven't worked it out. Because we're having difficulty showing that A intersect B is empty, but if we show there's a contradiction where an element appears, and we know
Right.
A minus B equals A, then we know that's going to be a problem.
Exactly. That's the best approach, because proving something is empty is not easy, because you want to prove that something, there is nothing in it. So a good approach would be, you know what, let us assume there is something in it, and then build a contradiction. Are you with me? So a lot of times you want to show that something is empty, it's like something does not have anything in it. Showing that it does not have is sometimes hard. So we say, okay, let us assume there is something in it. And all the idea that you guys building, whether it was Chris or Kai, we're going to make them into a very, very sound logical argument. So we're going to do this proof. Actually, we can do it by contradiction, or we can do it by contrapositive. Since you guys talked about contradiction, let's do that. So we're going to do proof by contradiction. Why? Because I want to show it's empty. So it's problematic. So let us remember what's the setup. Proof by contradiction. Okay, let's see what it is. What does that, what's the proof by contradiction work? Remember, this is my hypothesis always. And this is my conclusion. The proof by contradiction, we assume that we're going to assume A minus B equal to A, the hypothesis hold, and the conclusion is false. How can the conclusion be false if the intersection is not empty? So now I'm working with something. I don't have to hit my head against the wall or showing that it is empty. Now let us work with that. And now I'm going to bring both ideas, Kai and Chris, and make them into a solid argument. Okay, what does it mean A intersect B is not empty? So if A intersect B not empty, what does this mean? That's my assumption. I want to get to a contradiction. If it means there exists X in the universe such that X is in A and X is in B. Who can finish my argument?
But by the definition, or so that's we have that from the definition of intersection, but by A minus B equals A, B is not, or X is not an element of B.
And X is an element in B.
Yeah, no. So we have that, but from our assumption contradicts that because A minus B equals A. Oh wait, no, I'm making a jump.
You're making sense. You're making a lot of sense.
Because the A minus B equal to A, so A cannot be in the A and the B in the same time.
How are we going to write this correctly?
If the
X is in A and A equal A minus B. So X is in A minus B. Correct?
Yep.
So X
It's not in
It's
B.
not in B. But by assumption, we have X in B because I assume the intersection is not empty. So now we have X is in B and X not in B, which is definitely a false statement, which is definitely a false statement, which is false, which is a contradiction. We cannot have both at the same time. Hence, our assumption is false. So if A minus B, so it's very logical, but now what we're trying is to make it into a good solid mathematical argument. So if A minus B is equal to A, then the intersection has to be empty. Okay. So we actually use contradiction because whenever you want to show something is empty, as one of you said, it's kind of hard. So assume it's not. By assuming not empty, it gives me something to work with. It gave me an element to work with. So if this X is in A and B, okay, if it's in A, it cannot be in B. If it's in B and not in B, then we have our contradiction, right? So this is an example slightly different than the other ones, where we have to be used, contradiction, or sometimes you have to use whatever, contrapositive. So everything we've learned about proof is actually right there. We can use them again if needed, Right.
So you're saying, so that's why contrapositive works here as well, because we have the advantage that we're assuming it's empty, so we don't have to worry about finding out it's empty, because we're starting, no, you flip it, so it's actually, yeah, never mind. It gets rid of the empty problem. Yeah, the contrapositive flips it, so you don't have to worry about it. I'm talking about if we were to do the contrapositive.
No, it's very much the same proof.
Yeah, because you're just saying this has these elements, and then you go from there.
Right.
You just start from one other end.
Exactly, but then contrapositive also a very good idea. I mean, you can, but you guys talked contradiction, so I went along with you.
Yeah,
because contrapositive will assume this is not empty.
Right.
It gives
so you have the same
immediately
advantage.
an element. Go ahead.
I was just saying you have the same advantage at that point.
Exactly.
Because you're not worrying about that whole empty or not.
Exactly. Yeah. So this problem could be done either way. You can do it by contradiction and you can do it by contrapositive. So the main goal is to eliminate this issue of empty. So I need something to work with. And contradiction or contrapositive will give me this something to be able to work with. All right? Okay. So I will give you another problem along those lines, but in your homework. So I will not do it in here. The last thing I would like to finish this section with is just by actually stating all the property of sets in a big box. So you guys should actually almost memorize them. And then I will give you a small problem where we can use them. So the last part has nothing to do with those proof, but I'm going to summarize all the properties of sets. So all the algebraic properties of sets that every math student should know, algebraic properties of set. And you will know in a minute what I am talking about. Okay, it's a summary of all the algebraic. So as I say them, you guys will tell me the names of those properties. So suppose you have two sets, let ABC subset of a universal set U. Okay, so that's my, okay, so what do I mean by the algebraic properties? So let me write them down. I hope I don't forget everything. Okay, so if I take a set A, union, very simple one, union the universe. What should I get quickly? I want answer to every question I ask. Okay, the first question. So ABC are all subset of a universe. It means I have a universe and A, B, C are in it. Question number one, if I take A union the universe, what should I get?
U.
I get the universe because A is a subset of it. If I take A intersect the universe, what should I get? A. If I take A intersect the empty set,
Empty set.
A union the empty set,
A.
A. Okay, so if I take everything in A, union, nothing. So I get everything in A. Now, the other properties of set that I didn't talk about, but I thought it's like kind, is A union B is B union A. And A intersect B is B intersect A. What do we call this property? It makes sense. If something is in A or B, it means if it's in B or in A. What do we call this property?
It's commutative.
That's commutative property. So union and intersection are commutative operation. Now, the second operation that I proved in class, and I urge you to go over the proof. If I take A, and I said it's like numbers, union B intersect C, watch, there are parentheses, and I have two operations. So this is A union B intersect A union C. And this definitely should remind you what we do with number. If I take 2 times, or like A times B plus C, I distribute A times B plus A times C. So that's the idea. And this property is called distributivity. Distributivity of the union with respect to the intersection. This we proved in class, so you can go over the proof. I urge you to do that. And then the intersection also, so this is the distributivity property, is also distributive with respect to union. A intersect B, union A intersect C. Now, the other property is A union What do we call this property? Watch carefully. I'm not changing the operation here. Very important. Here I'm changing. Here I'm not. So it's union and union. So I just switched. What do we call this property? Back to you. So I'm saying if you have A plus B plus C, it's the same that A plus B plus C. You
The
guys
associative
remember?
property.
That's the associative property. Okay. And because of this, if I have the same operation, I can even neglect parentheses. But remember, I have to have the same operation, union, union. Sometimes we don't need parentheses because we know whether we take this union that or A union this, I get the same answer. So we allow ourselves to basically remove parentheses as long as we have the same operation. That's why we can write 2 plus 3 plus 5 without worrying about parentheses, because it doesn't matter whether you add them this way or you add them that way. Now the same thing holds definitely for intersection. Sets. Okay. Now, the two other property important for sets. That's very important, and I've talked a lot about it in the last lecture, and we prove it. And it has to do with De Morgan's law. The complement of the union is the intersection of the complement, which I've read it for you. X is not in A union B. It means it's not in A and it's not in B. And I urge you to think about that. And then the same go for here is A union to complement. And we call this De Morgan's law. So all those properties you should be able really to know that. Now there are other simple properties that, and the last one is, it's not a property, it makes sense. A minus B I will write it and see if it makes sense to you. Is the same thing as A intersect B complement. It is useful sometimes. Does this make sense? Does this make sense? I don't know if I proved it. I don't think so. Does this make sense? What's A minus B? Then we'll do the picture for it. It means if X is in A minus B, it means it's X is in A and not in B. It means it's in A and not in B means it's in B complement. And vice versa. If it's in A and in B complement, it means it's in A and it's not in B. Okay, so that's it's not, it has not, doesn't have a name, but it's really a very useful property to use. So let me finish this with a small application to those ideas. So these are the algebraic properties of set that you should definitely, that's like, knowing the ABCs of set, we should know. And I'm gonna do one simple problem, not more. I want you to, we're gonna do the following. Use the algebraic properties of set. Properties of set to prove the following. I'm going to do one today and one next time. So suppose there is something I proved last time using what we called element-wise proof. So, and I showed you that A union B minus A is the same as what? Do you guys remember? I have a universe. I take A and I add to it B minus A. Do you remember what we got? We got A union B. Okay. And last time we proved this equality using element-wise proof. It means we started with an element in here. We proved that it is in here. Go over it. We started in here. We proved that it is in here. So we did that. Today I'm going to do it in a slightly different way, and which is more mechanical. That's why I don't like it. I keep it to the end. It's very mechanical. So what do I mean by mechanical? Right. Mechanical, it means we use the algebraic properties to show this equality instead of using element-wise. It means starting an element here, proving it here, or an element here, or proving it here, which is actually mathematically the other one is what you guys will be using in the future if you keep working math. All right, let's see what I mean the algebraic property of set. It's the following. I'm going to rewrite this as A union. Instead of B minus A, I can rewrite this as B intersect A complement. Okay, because logically, if it's in B minus A, it means it's in B and not in A. Now I'm gonna distribute, use the distributive properties of the union with respect to intersection. So I'm gonna use the distributive property. It's gonna give me A union B, A union B intersect A union A complement. Okay, I'm almost done. This A union B intersect. What's A union A complement? I take A and its complement. What do I get? Quickly, guys.
Would it be empty set?
On the board, I would have like pushed, pounded the board. I can't pound the board now. I pounded my mouse. A union A complement. Just think Venn diagram. Think Venn diagram. Let's say complement.
you'd get the universe and then you intersect a union
Right.
B with the universe and you get A union B.
That's the universe. A union A complement is the universe, because remember that's a union. A union A complement is everything in A or not in A, but that's the whole word. Either it's in A or nothing. There is an or in here, not an intersection. It's an or. Now, if I take A union B intersect the universe is everything. So if I take any set, that's my universe. If I take any set in here, intersect the universe, it's going to give me my set back. Okay, which is going to give me A union B. Okay, and we call this an algebraic proof. So we call this an algebraic proof, and the way we did that last time, when I did, we call it an element-wise proof, which is starting an element here and landing here and vice versa. So the algebraic proof are fun, they are easy to use, but I do not emphasize them, especially at the beginning, because they are very limited. I can only use them to prove something like this, but I can never use algebraic properties to start proving something like about the Cartesian product or something about power set or a lot of other properties of sets. All right. Okay, I stop here. You guys will have a homework dealing with sets. I will try to get it out for you by tomorrow, and you guys owe me a homework tomorrow, and it will be due next Wednesday, so you will have time for it. I urge you to go through the 3 lectures concerning sets. Take every problem we did on the board and do it by yourself. Do it by hand and see if you are, getting them correct. After you do that, start doing the homework. Okay, any questions? All right, if you have questions, you guys, about the homework that I gave, I have office hours from 3:30 to 4:30, so please stop by and ask me any question you want. Otherwise, have a wonderful Thanksgiving break. Okay, bye-bye.
Take care, enjoy your break.
Sure, any questions? All right, bye-bye, guys.